Hello, my name is Prasad Sisla. I am presenting this talk on this paper on linear time decidability of differential privacy of programs with unbounded inputs. This is a joint work with Rohit Chadda and Mahesh Viswanathan. The main contributions of this paper is an automated model for describing differential privacy algorithms, certain differential privacy algorithms that take unbounded sequence of inputs and generates outputs interactively and uses a privacy parameter epsilon. Now, it gives a necessary and sufficient condition for differential privacy of the algorithm modeled by these automata, and it presents linear algorithms for checking these conditions. We start with well-known example of this part of sparse vector techniques. And essentially, sparse vector techniques an algorithm which takes a sequence of query values and a threshold constant t and outputs the first I such that q of I is greater than t. Instead of actually working with the actual values, the algorithm works with the noisy values of the threshold and the queries. So initially, the samples from a Laplacian distribution with mean the threshold value t and the scaling parameter epsilon by 2 and stores in the noisy way t. And then it goes through each query value, and for each query value it generates the noisy version of the query value as shown here, and it checks if the noisy version of the query value is greater than the noisy version of the threshold. If so, it then outputs top and exits. Otherwise, it outputs bottom and continues. Now, the automaton for modeling this activity is given in this figure. As you can see, the automation has two types of control states. One represented by rectangles and another represented by circles. The rectangles are called non-input states and circles are called input states. And each of these states has two pairs of constants. In the first pair, the first component of each pair is a scaling constant and second component is the mean. Similarly, the second pair. For this automaton, you don't need the second pair. And each transition has three components. The first component is a condition. The second component is the output that is generated when the transition is taken. And the third component is a Boolean value, true or false. And then the automaton also has a storage variable x, and in which it can store some values. So when it is in a non-input state such as Q0, it basically samples from a Laplacian distribution with mean 0 and scaling parameter epsilon by 2, and it stores this value in the temporary variable in sample, and then it checks the condition of the transition leaving out of Q0, and which is true, and therefore it takes the transition. And during this transition, it generates the output bottom, and then the third component says that the in-sample value should be stored in the variable x. So it stores it in x, and then it transitions to state Q1. When it is in state Q1, it samples from a Laplacian distribution with mean 0 and scaling parameter epsilon by 4, and then adds to it the input value that it has read and stores it in the temporary variable in sample. And then it checks if which of the outgoing transitions are enabled. If the self-loop transition is enabled, that is in sample is less than x, then it takes the transition and it outputs the bottom. And since the third component is false, the value of x is not updated. On the other hand, if the transition to Q2 is enabled, that is in sample is greater than an x equal to x, then it outputs top and transitions to Q2 and terminates. Now, if it transition leads back to Q1, then it again samples from the Laplacian distribution with those parameters and adds it to the next input value and stores it in sample, and it repeats this process. Now, there is a modified version of SVT called numeric sparse, which is almost identical to SVT, except that when the QI is greater than T, that means for the first I, instead of outputting I, it's supposed to output QI. Instead of, as usual, it works with the noisy values, and as you can see, the algorithm is almost same, excepting that the scaling constants in each of the Laplacian distributions are different. And when the noisy Q is greater than noisy T, instead of outputting I, it outputs a freshly sampled value from a Laplacian distribution with mean the current input and the scaling parameter epsilon by 9. Now, the automaton corresponding to the numeric sparse is almost identical to the automaton for corresponding to the SVT, excepting that the scaling parameters corresponding to each state are different, and the transition from Q1 to Q2, the output of it is in sample prime. Here, in sample prime is the value that is obtained by freshly sampling from a Laplacian distribution with mean 0 and scaling factor epsilon by 9 and adding it to the current input value. Now I give you some definitions of the automaton. An assignment transition is a transition which assigns in sample to the variable x, and we also require determinacy condition for the automaton, which says that all the transitions that are leaving from any states, their conditions should be disjoint and the outputs should be different, and at most one of those outputs can be a real output, that is either in sample or in sample prime. Now, a path is a sequence of consecutive transitions of the automaton augmented with inputs and outputs. Remember that the transitions of the automata do not have any inputs. So we augment the transitions with inputs. And of course, we also augment with outputs. When the output of the transition is a discrete value, then the augmented output should be equal to the transition output. When the output of the transition is a real value, the augmented output is a real interval. For any path row, in sequence row, and out sequence row are the input and output sequences in the path row. Now, if you have two input sequences U and V, we say that they are adjacent if they are of the same equal length and corresponding values in these sequences differ by at most 1. Now, if you consider two paths, we say that two paths are equivalent if they differ only in input values. That is, all the transitions, sequence of transitions are the same, only the input values are different. Now, for a path row starting from the initial state and for a given value epsilon 0 of epsilon, we define a probability of rho with respect to epsilon and represent it as probability rho of epsilon 0. And this is essentially going to be the probability that the automaton generates the out sequence of rho when it is fed a sequence of query values given by in sequence of rho. Now we have the definition of epsilon differential privacy as follows. Automaton A is d epsilon 0 differentially private if and only if for all equivalent paths rho 1, rho 2 starting from the initial state such that the sequences of inputs in rho 1 and rho 2 are adjacent, it is the case that probability of rho 1 with respect to epsilon 0 and probability of rho 2 with respect to epsilon 0 differ by at most a factor of e to the power of d times epsilon 0. Now, we say that automaton A is differentially private if and only if there exists a constant d greater than 0 such that for all epsilon 0 greater than 0, A is d epsilon 0 differentially private. Now we define a new concepts like leaking cycle and leaking pair. First, a cycle is a path starting and ending with the same state, and a leaking cycle is a cycle that has a transition which is an assignment transition later followed by a transition whose condition refers to the variable x. Now, A cycle is an L cycle if it has a transition whose condition is in sample greater than less than or equal to X. And it is a G cycle if it has a transition whose condition is in sample greater than X. Now a path is a AL path if all assignment transitions in it has condition in sample less than or equal to X. Now AG path is defined similarly. A leaking pair is a pair of cycles C comma C prime such that C is a L cycle and C prime is a G cycle, and there is an AG path connecting a state in C to a state in C prime, or C is a G cycle and C prime is an L cycle, and there is an AL path connecting a state in C to a state in C prime. Now we define the well-formedness of an automata. In an automata with only discrete outputs, okay, that is, it has no continuous outputs or real outputs, we said to be well-formed if and only if it has no leaking cycle reachable from the initial state and it has no leaking pair of cycles C comma C prime such that C is reachable from the initial state. Our main theorem of the paper says that an automata with only discrete outputs is differentially private if and only if it is well formed. The proof of the theorem is non-trivial in both directions. There is a linear time algorithm given in the paper that checks whether an automaton with only discrete outputs is well formed. There is a linear algorithm that computes a constant d for a well-formed automata A such that A is d epsilon 0 differentially private for all epsilon 0 greater than 0. Now, the SVT automaton that is given in the beginning is well-formed and therefore is differentially private. And the SVT automaton that you get for many correct versions of SVT algorithms are also well formed. In all the above cases, the computed constant D matches the published bounds, the computed constant computed by our algorithm. Now, if you look at the following automaton, A sort, which is almost equivalent to SVT automaton, excepting that the self loop in the state Q1, the third component of it, is the value true instead of being false. Now, this automaton basically checks if the given query values are in descending order, but when it gets the first query value whose value is greater than or equal to the previous query value, it outputs top and terminates. Otherwise, it keeps outputting bottom. Now, if you look at the automaton given in this slide, you see that it has a leaking pair. It has the first cycle is an L cycle, the second cycle in it is a G cycle, and there is an AG path. And therefore, this has a leaking pair, and therefore, this automata is not well formed. Now, the well-formedness definition is extended in the paper to automata that have both discrete and real outputs. The main theorem relating well-formedness to differential privacy is extended and proved in the paper. The automata for numeric sparse is well-formed and is differentially private. There is a linear time algorithm that checks for well-formedness of such automata. Conclusions: we gave an automata model for describing differential privacy algorithm, and then future work, and then we gave sufficient necessary and sufficient conditions for well-formedness and things like that. As future works, computation of a tighter constant D and making the automaton model more expressive. Related work, please see the paper.